Hi, in this video we're going to look at the following problem. We're going to consider the expression p cubed plus n squared, where p is a prime number and n is an integer, well, positive integer, non-zero. It doesn't actually matter if it's negative, but we're only going to think about it being positive right now. And we want this expression to be a perfect square. So in general, there are infinite many values for n which will have a solution. There'll exist a prime that will make it a perfect square. But most of them will only have one prime that'll make it a perfect square. It turns out there's one value exactly for n for which there'll be two distinct primes, which result in a perfect square. And we're going to find those now. So this, of course, is equivalent to considering the Diophantine equation. P cubed plus n squared equals m squared, where n is also an integer. M is also an integer. So we're going to do this by dividing it into a few cases. So for case 1, we will have where p divides n. In which case, we could write n equals p times a for some integer a. And of course, if p divides n, then p must also divide m. And I'll leave that up to you to figure out why. It's pretty obvious. So we have m equals p times b for some integer b. So if we substitute in pa and pb, we get p cubed plus p squared a squared equals p squared b squared. And now we can just divide through by p squared, which reduces this to p plus a squared equals b squared. And if we subtract a squared from both sides, we get p equals b squared minus a squared. And then, of course, we can factor this as a difference of two squares. So we have a prime number is equal to b minus a times b plus a. And since p is prime, there's only one factorization possible, 1 and p. And since a and b are positive integers, then a plus b is the bigger number, so we know that b minus a equals 1 and b plus a equals p. So we can rewrite this a little bit and say that b equals 1 plus a. And then if we substitute this in over to our expression for p over here, then we get 1 plus 2a equals p. And now if we simply solve for a, this will give us a equals p minus 1 over 2. And now we substitute this back into for n. So we multiply by p. This is a, so if we multiply by p, we'll get n. So we have n equals p times p minus 1 over 2. So for a given p, and we're doing this a little bit backwards since we're finding n from a p now. So for any given p, so if we have n equals p times p minus 1 over 2, then our expression up there should be a perfect square. And you can test this and see that that will always be true. So if you pick a prime number p, put it into this expression for n, then p cubed plus n squared will result in a perfect square. Now we will consider the second case where p does not divide n. So case 2, p does not divide n. I know it looks like an x, but it's a not divide symbol. So in that case, we have p cubed plus n squared equals m squared still. And we're not going to do any fancy substitution, so we'll just factor this. We'll move the n squared over and factor it directly into difference of squares. We get p cubed equals m minus n times m plus n. And we'll see, actually, case 1 could have been considered a subset of case 2. I found it easier to handle it as a separate case. So we have a p cubed, and this can only be factored essentially in 2 ways. We either have 1 times, if we're talking about factored into 2 factors, we either have 1 times p cubed, or we have p times p squared. Now, notice if we take the second factorization, if we take this one, then that means p divides both these terms. And if p divides both those terms, then it must also divide the difference of those 2 terms, which means that if p divides m minus n and p divides m plus n, then we could take this one minus this one, then p divides 2n. So then we have either, so then that means that either p equals 2 or p divides n. So we have 2 cases, 2 more subcases here. Notice that this case is our case 1. We've already handled that, so we rule that one out. And you could do a quick check with p equals 2. It's quite easy to check for p equals 2. You'll see, you'll get an n value for, you'll get a value for n, and you'll see that there's only there's no other p that'll work for that n. That's pretty easy to check to rule out p equals 2. So we won't go through that here, but I will show the other case, which is where we have this factorization. And again, with this factorization, we know that m plus n is bigger, so this will give us that m minus n will equal 1, and m plus n will equal p cubed. So we're pretty much going to do what we did before. We'll just set m equal to 1 plus n, and then we'll substitute that in here. So we get 2n plus 1 equals p cubed, which will give us p cubed. We're solving for n now. N will equal p cubed minus 1 over 2. So what this means is that in general, we could, for any p, we could pick this n, where p won't divide that n now in that case, and that n should also work. So if we think about what this means for our problem, that we want 2 different primes that'll have the same n. So we want 2 different primes, one from this formula and one from this formula here, to result in the same n, which means that they should be equal. So we want picking a prime for this formula, and we want picking a different prime for this formula to result in the same n. So if we call our primes p and q, then what that means is we want p cubed minus 1 over 2 to equal q times q minus 1 over 2. So if we find 2 primes p and q which satisfy this Diophantine equation, then we've solved our problem. And we'll see that there's only one pair of primes that satisfies this, which is why there's only, and we get one n from those primes, which is why there's only one n that has that. And of course, we can directly multiply out the 2, so this reduces directly to p cubed minus 1 equals q times q minus 1. So everything reduces to solving this Diophantine equation. So I'll write it up again. So I wrote p cubed minus 1 equals q times q minus 1. Oh, we don't have over 2. Right, so we can factor the left-hand side. I'm just going to switch the order here. So we're going to write q times q minus 1 equals p minus 1 times p squared plus p plus 1. This is just standard factoring of the difference of cubes. And note that, we're just going to note real quick that p squared plus p plus 1 is obviously greater than p, which means that q times q minus 1 is greater than p times p minus 1 because of that. Right, because if I put p in here, right, then I've made this side smaller. If I put p in here, then I made this side smaller, so this holds, which of course quite easily shows that q is greater than p. So we just have that as a simple thing that'll make it a little bit easier. And because of that, then we know that q, since q is bigger than p, q cannot divide p minus 1. Right, since q is bigger than p, q cannot divide p minus 1, so q, the prime number q, must divide this expression instead. So we know that q divides p squared plus p plus 1. So what we're going to do now is we'll just, since it divides that, we know that q times something equals that. So we're just going to say that p squared plus p plus 1 equals q times k for some k. That's what it means, that q divides that. And now we can substitute that back in. We'll take that up to here. So we have q times q minus 1 equals qk times p minus 1, right? And of course, I can just divide out the q's here, because that's not a problem. So we have q minus 1 equals k times p minus 1. And we can multiply out the k here, which equals kp minus k. So now what we're going to do is we're going to multiply everything by k, just so we could do a nice substitution again. So we have kq minus k equals k squared p minus k squared. And now we have this kq term again, which we know is equal to p squared plus p minus 1. So we just put that right back in. So now we have p squared plus p plus 1 minus k equals k squared p minus k squared. So now we are going to make this into a quadratic equation in terms of p. So I'll just gather all the terms together. So we have p squared And then we're going to have plus, and what do we have? We're going to have a 1p here, and then a minus k squared. So it's going to be plus 1 minus k squared p. And then plus, and then all the constant terms together. This will be a positive k squared minus k plus 1, so plus k squared minus k plus 1 equals 0. So if we're going to solve this quadratic equation, we can just look at the discriminant. What do we need? We need a discriminant to be a perfect square if we want this to be an integer, right? So solutions for this, p is a prime, it must be an integer, so that's a requirement. So our discriminant will end up being 1 minus k squared squared minus 4 times k squared minus k plus 1. And this expression has to be a perfect square, because this is what will be under our square root. And if we multiply everything out and simplify, we end up with k to the 4th minus 6k squared plus 4k minus 3. So we want that expression to be a perfect square. So we'll take that to the next page. And we'll do some nice easy tricks here by squeezing it between some perfect squares. So I'll write that up again. We have k to the 4th minus 6k squared plus 4k minus 3. And this we want to be a perfect square. So first we'll notice, and we'll just call that our delta. So first, I won't go through the details. It's quite easy to figure out that this is equal to k squared minus 3 squared plus 4k minus 12. And we see that that's always positive. And so if this is, if k is bigger than 3, so if k is bigger than 3, then this is then positive, right? Because then 4k is bigger than 12, so then that's also positive. So then we get two positive numbers. This is positive always because it's a square. And if k is bigger than 3, then this is positive. So then that's a positive, then this right-hand side is a positive number. So we say that for k bigger than 3, since this is positive, that delta is bigger than k squared minus 3 squared for k bigger than 3. Okay? So that's the first step. And now we just check this is for k bigger than 3. We have also, we can also show that with a little bit of other algebra that delta is equal to k squared minus 2 squared minus, and I'll leave the details of the algebra to you, and then in parentheses k minus 1 squared plus 5 halves. And we see that this whole expression here is always positive, right? Because we have a square inside and we're just adding something to it. So this is always positive. So we're always subtracting a positive number. And so that the delta always has to be less than this, because this is what delta is equal to, so it's always less than that. So we know that delta is less than, always strictly less than, k squared minus 2 squared. So for k bigger than 3, what we have is that k squared minus 3 squared is strictly less than delta, which is strictly less than k squared minus 2 squared. And these are two consecutive perfect squares, and so there cannot be a consecutive perfect square between them. So this means for k greater than 3, no solution. So the only thing we have to do is check by hand, and if we check by hand, we will see that, and all we have to do is check 3 cases, k equals 1, k equals 2, k equals 3, so check k equals 1, k equals 2, k equals 3, and we see that only solution for k equals 3. And I'll leave those details to you as well. It's pretty easy just to check that by hand real fast. All right, so for k equals 3, we end up with delta equals 36. And that will give us that p equals, well, if you work it out, you'll end up with p equals 7. And if you then put that back in, you can use that very quickly to find q. You'll get q equals 19, and that will give you that n equals 171. So this is the answer. N equals 171 is the only n that will result in 2 unique primes that both will result in a perfect square. That will be 7 and 19.